All right, this section is going to seem really easy compared to anyone who's taking Algebra 2 for the first time and has never seen some of this stuff before. This is about inverses. This is technically lesson 7. And we did inverse in a major preview way, actually more than preview way, when we did the logs unit, when we were talking about logs and exponents. And the whole purpose of that at the time was, if you remember, inverses were important because a logarithm basically is an inverse of an exponent. So that's kind of how you have to teach logarithms in the first place. So again, this lesson was written with someone else in mind, people who would have been looking at this for the first time here about inverses. So this is going to seem kind of elementary compared to the way you've already learned about it. So, for example, we're talking about a function that takes an input and then spits out an output, and then we take that output, put it back into some other function, and it comes out, and it turns out to be the same thing we started with. So basically that the second function undoes the first function. The example that they have is kind of rudimentary. Input value squares it, subtracts 5, and sends out the result. You can think about that in terms of notation a little nicer than the way they have it here, a little more standard, I guess, because we are kind of a little more sophisticated than this at this point in our algebra story. Takes an input value, squares it, subtracts 5, and sends out the result. So that's it. So write an equation. Oh, we did that already. That's what this is saying. This is the x squared minus 5 machine. If we put 3 in there, what's going to come out is going to be 9 minus 5, which is 4. And then they have already done this for us. They put 4 in, and they're basically saying there's going to be some kind of function that takes whatever it is that x squared minus 5 spits out and figures out how to make it 3, which was the input before all of that started. So the question is, what do we do to 4 to get it back to being 3? Well, you might realize that when we did this back in the logs unit, we started out by doing this kind of thing because we need the inputs and outputs to kind of change jobs if this is what we're going to be talking about. So we do the old switcheroo there, and then we solve this for y. So now I'm going to say something like y squared equals x plus 5, which feels like we reversed one of the processes, and then the other process we have to reverse is the squaring has to turn into square rooting. So if I take 3, I add 5 to it. No, wait, that's not going to work. If I take 3, sorry, if I'm going to take the 4 and put that into the inverse function. So the 4 is going to go in there. If I put 4 in there and I add 5 and I square root it, lo and behold, it does turn out to be 3. So that takes us back. That takes the 4 and turns it back to 3. The first function took 3 and made it into 4. The second function took 4 and turned it into 3. Yeah, this one's almost too easy. I'm definitely not going to spend time doing this on video. We might do this in class. I might realize that that's even too easy for class. So this is the story on how to make an inverse. Like I said, you've done this before. Switch x and y basically. And the other thing that we're going to figure out, and I'll talk about this in class, I'll reiterate it because we did do this back in the log days, is in the end we end up making, if we're going to talk about the functions of x and f of x and the inverse are going to be reflections across that line. And the fact that they're reflections, that's really the reason why it's showing up in this unit, which is about transformations. And this is just another example of a transformation. All right. This may look a little too big for my taste. Oh, wait, I'm making little dots everywhere. All right, consider this graph. Sketch the inverse. Okay, this is a little bit different and in some ways harder than what we did in the unit or the lesson on logs. So the original, and because we don't know the rule for this. Like, it's one thing when you know the algebra function coding for how the inputs and outputs work, but this is just one of these weird things where we just have this kind of conceptual notion of what the inputs and outputs are. So if I'm going to try to figure out the inverse of this, all I can do is really say, well, if 9 goes in and 3 comes out, then if 3 goes into the inverse, negative 9 must come out. In other words, I'm just reversing all the x's and y's. There's going to be a bit of a problem here when we get to the stuff on is this a function or not because of what we see here, but they're not really asking us about that right now. They're just kind of asking, go ahead and sketch the inverse and see what happens. So yeah, because we're gonna some of that other stuff you may notice comes up there. Sketch this graph. Okay, I'm gonna pause it and do it so you don't have to watch me struggle with all that. Bam, there it is. Yeah, that would have been painful to watch me do all that. And you notice it is a reflection across the line here. This is the y equals x line, which we just talked about. That's what happens when you switch the y's and the x's. You get that kind of thing. And it makes this nice symmetrical reflection picture like we're used to seeing. So that's great. The question is that thing a function? Oh, is f of x a function? This is f of x. And this is this kind of thing. Oops, yeah. Remember that notation. It's going to come up in a minute. Is f of x a function in the first place? So the black thing that's printed in the first place, we would say yes, because it passes the horizontal line, vertical line test. It's been a while, right? This is like the first day of this unit. Passes the vertical line test. Is the original black thing a one-to-one function? And we'd say no, because it fails the horizontal line test. So just a reminder about that stuff, because this is good, because it's coming up for the test. Is it a function means is there for every input, is there exactly one output? So for every x, is there one y? And that's what vertical line test is about. One-to-one is kind of the switcheroo on that for every y, we can tell exactly where it came from. And we can't on this one because there's some horizontal lines that do cross twice on the black one. So is the inverse of function is equivalent to this question above? Those will have the same answer because notice, or if that isn't readily obvious, look at the red function and look at the the vertical line test for that. We're definitely going to fail the vertical line test on the red one. Okay, we can talk more about that in class if you need to. All right, this little graph. Sketch the graph of the inverse on the same grid. I'm going to pause so you don't have to suffer through that. I'll be right back, and bam, there it is. This one looks a lot better in terms of is it a function or not. And, well, let's answer the questions in order, and I'll talk about why. Do you notice reflective symmetry over the line y equals x? You're supposed to notice that. Like if we do draw that thing, we see reflective symmetry. Is g of x a function? That's the red one. This is yes. Oh, no, sorry. That's the black one. The black one is g of x. Is that a function? Yes. Is it one-to-one? Yes. And is the inverse, which is this thing, is that one a function? Yes. Again, these two questions will always be equivalent. Is the original one-to-one, and is that, that's saying the same thing as is the inverse a function? So there we go. And guess what? That's exactly what's in the box. You can read that again. All right, consider this point. I'm trying to decide, do we want to do this in class or not? Yeah, I've decided this is not worth video time, making you do this. We will do this in class, if at all. Proving that a thing is an inverse. This did come up in the logs. This is about, does it really this is kind of how we tell for sure, does it really undo the thing for all x? If we put in, well, let's talk through this. This is saying, if we put 2 into this function, something comes out. We see if that something, when it came out, does it go into this thing we're claiming is the inverse, and does it give us the 2? Did the 2 come back after going through the forwards function and the inverse backwards function? Did all of that work? And we can try it with one number at a time. This is plus 3 minus 3. This is kind of silly. 2 plus 3 is 5, so we stick 5 into the minus 3 function, and we get what we started with. G of f of 2 is 2. And if we switch the minus 3 function and the plus 3 function, kind of like this, so one of these is f of g of x, and one of these is g of f of x, you notice. Put 2 into the x minus 3 function, you get negative 1. Put negative 1 into the x plus 3 function, lo and behold, you get 2. So f of g of 2 is also 2. That's that. So we've just proven that it is an inverse when you start with 2. It doesn't prove that it's an inverse all the time. To prove that it's an inverse all the time, we'd have to start with x, see what comes out, put that whatever comes out back in here, and see if it turns out to be x again. As you know, we have done that plenty of times. And that's what this is talking about. Okay. So just here's another example of a reminder of how we did that back in the unit on logs. Remember, you do have to check both of these. I know people are annoyed by that, but yeah, you have to say if putting it into one and then the other gives you what you started with, and if you do that in the reverse order, it comes out what you started with. So f of g of x should be x, and g of f of x should be x. So let's just do one of the examples. They both look equally interesting or non-interesting, so I like to kind of do this. We will do the second one in class, but the first one we'll do now. So f of, now I have a yellow pencil. This is weird. F of g of x. Let's see what that is. Well, that's f of Wait, what's happening? So I did that thing where my hand hits the button. Why is it not red anymore? Okay, sorry. I'm really trying to make you not suffer through too much silliness on these videos. All right, 3x minus 2. And so f of 3x minus 2 is going to take 3x minus 2 as the input right there. So 1/3 3x minus 2 plus 2. Order of operations states that I need to deal with the 1/3 first. So this is x minus 2/3 plus 2. This doesn't look like it's going to work. This is not equal to x. This is x plus some number, right? This is x plus, I don't know, 2 plus 6 is like 4/3 or something. And that's not x. So for my money, we can stop right there and say, no, these are not inverses because we didn't get x when we stuck x into G and then that input into, or that output into F. So we're done. It does have to be more interesting. Okay, I changed my mind. We will do this one because I'm guessing, I can't erase that because, well, now it's working. Because this one's probably going to turn out the other way, and I kind of want you to see both ways on this video. Okay, so let's do f of g of x here. F of g of x here is f of 1/2 x minus 2, and so I put 1/2 x minus 2 in for that input, so 2 times. I'm just guessing this is going to work out just because of, worksheet design. Why would they give you 2 no's in a row? Which is not a good way to live your life. Like, you shouldn't really plan like that's always going to be the case. Like, just because there's 2 examples and there's 2 possibilities, and one works out one way. No, okay, so that one worked out to be x. So I'm not done. Now I have to continue and check g of f of x. Let's see if it turns out to be x. G of f of x is g of 2x plus 4. Now I put 2x plus 4 in there, and I get 1/2 of 2x plus 4 minus 2. Do the distributive stuff, and I get x. And since they are both x, I say yes. And saying yes is an important part of this question, because the question is a big yes-no question. Verify if they are or not. So you have to say if they are or not, and they are. So we're done there. I think this looks more interesting. Finally, something interesting. Should we do this in class or should we do this now? We can start this. Okay, so it's kind of a non-standard question. All it's telling us is that, I'm going to use capital A, that's her function. If we put in 3, it spits out 7. If we put in 4, it spits out 9. If we put it, this reminds me of that pattern thing we did in class, at -5. So we want to try to turn this crank in the opposite direction and feed it the 7 so it spits out the 3. We're going to figure out what is the rule for going kind of backwards on this machine. She wants a machine, we're going to call it A inverse, that, I guess all we know about it is if we put in 7 or 9 or -5, that it's going to spit out 3 or 4 or -3. And the task is, can we write an equation for that? Being able to write that equation is actually not the biggest deal in this unit, but I just wanted you to know in this video that that's what they're asking. So I'm going to say this, and that's what we will do in class. This skill is a little more universal, which is in general finding the inverse, which they talk about in the first page of these notes, but let's actually do it. So I guess what maybe the important thing here is to know what the directions are saying. When it says find the inverse algebraically, that means do the x and y switch and see how, and actually find out what it is. The other question is, here's 2 functions, verify whether or not they are using composition. That's the one where you have to do f of g of x and g of f of x. This one is the y-x switcheroo solve, kind of find it. And I guess maybe the hint on that is, notice in this, they're just giving you one at a time. Problem A, there's 1 function. If they give you 2 and they ask, are these inverses, then you got to do the f of g of x business. But this is the one I think you guys think is more fun. Do this and solve for y. So, whoops, towards y. I end up with y on this side, which is okay. I've divided everything by 4. I forgot the x. Okay. I don't know if I need to do all these. Actually, no. We can say both these for class. I'm not going to do either one of these. Okay. Here's the big so what summary on inverses. We call it an inverse if it's supposed to be the thing that undoes, or like sends backwards or changes that gives us a rule for how to take the outputs of a function and find what the inputs were. So you can say that in lots of different ways. And all these things are true. Symmetrical about the line y equals x, that just means if we graph it, and we graph the original function and its inverse, it's going to have this property where there's a line of symmetry at y equals x. That was not a great picture, but it wasn't terrible. It's a reflection across that line. All the points in the graph are switched, so if it's a point that's originally x comma y, then the point that's going to be on the On the inverse graph, it's going to be y comma x because it's about switching inputs and outputs. We denote it with this crazy notation with this -1 here. That does not mean anything about taking anything to a -1 power or a reciprocal or anything like that. It's just this means f inverse. It's kind of a stupid notation, but that's how they denote that. It was the same for sine, cosine, and tangent. If you had to find the inverse sine of something, we were not taking anything to a -1 exponent. It was undo the sine function. Go backwards on the sine function. It's only going to be, the inverse is only going to be a function if the original was 1-to-1. And that's if you think about how horizontal line tests and vertical line tests are kind of related. The domain of f of x is the range of the inverse, and the range of f of x is the domain of the inverse. I don't think that's come up yet in this video, but I don't think that's a surprise. We can talk about that if you have more questions about that later. But we've had lots of problems in here so far where you just kind of switch the things in the table, and that should make that make sense, I guess. To find the equation, you can switch x and y and solve for y. And to prove that they're, so yeah, one of these is find, one of these is kind of prove. To verify, yeah, sometimes this is called verify by composition. I'm just trying to reiterate the instructions that tell you which thing to do. Am I switching x and y, or am I plugging one into the other? This is the plug out one into the other. This is the x and y switcheroo solve kind of thing. Yeah, so that's what that means. Yeah, this last thing on extension, I really don't feel like we should do this on video. I don't think it's that important. I think it's, I'll tell you why, I guess, in class, but it has to deal with some things that we've already actually talked about in the log unit, and I know today is crammed up against review for the test, so I don't need to have you waste more time and get worried about this now. We will take care of this in class also. Okay, that's it.